Okay, so like I mentioned last time, today we're gonna spend like two or so slides just wrapping up the idea of one-dimensional conduction, kind of doing it the direct way, right? Which is set up your version of the heat equation in whatever coordinate system you're operating in, eliminate any terms you can, and integrate it to get your general solution, and then your constants of integration are defined by your boundary conditions. Okay, it's the same process regardless of what kind of system you're looking at, anytime it's one-dimensional and steady heat conduction. Okay, those other cases, multi-dimensional and transient heat conduction, stuff that varies over time, is going to be the topic of later chapters. But right, so far, or at least in the last lecture, right, we discussed this idea of the plane wall with heat generation and cylindrical conduction. There's not supposed to be an S there. Cylindrical conduction without any heat generation. So in the case with a plane wall, remember, because we retained this Q term here in the heat equation, when we integrate, that Q term finds its way into our general solution. We still, of course, have C1 and C2 as our unknown constants. And so the definition of our boundary conditions, whether that's a temperature or convection condition, allows us to find C1, C2. When we were dealing with cylindrical coordinates, okay, our heat equation, if we drop that Q dot and just assume steady 1D, no heat conduction, or no heat generation, then our version of the heat equation we're solving looks like this. Integration gives us this logarithmic distribution. So what that means is that if we have a temperature at some inner wall of a tube and some outer wall, we're going to get this logarithmic variation between the two. If the temperature outside is warmer, then it's going to look like this. So a couple of takeaways, right? In the plane wall, let's say we decided after the fact to say we decided after coming up with the general solution, we decided to eliminate that Q dot term. That Q dot's just right there. Chose to eliminate that Q dot. What would happen is that would go away and we'd end up with our linear distribution we had before. Okay, so this doesn't invalidate it's called the general solution for a reason. So if we don't have heat generation, right, we have this linear temperature variation between 2 points. And because it's linear, this means, right, the slope is constant. And by extension, that means that the heat flux is constant as we move through the wall. In other words, all of the heat going in one side has to come out the other side. Because those two sides have equal areas, the amount of heat per unit area also has to stay the same. In the cylindrical case, though, right, we still have all the heat that's entering the solid from this inner diameter here. All of that has to come out because the surface area at the outside is bigger, right? Then that heat gets spread out. So our Q double prime, our heat flux, decreases, and that's reflected by the fact that the slope here is higher, right? Meaning Fourier's law tells us that heat flux is higher, and it decreases as we move towards the outside. So remember, if we're given surface temperatures for any of these cases, if we're given the surface temperatures, TS1, TS2, very straightforward. Substitute to find C1, C2 directly, right? However, if we're given some other information about the temperatures, right, something other than the direct surface temperatures, for example, if we're not given TS1, TS2, but we're given the temperatures and the convective coefficients of the surrounding air, then solving for C1 and C2 basically amounts to adding some additional equations. Okay, and those additional equations are, we'd say, additional equations that basically amount to Q double prime, we'll say conduction is equal to Q double prime convection, right, at the boundary. And then we say, well, we know how to compute Q double prime conduction, right, from Fourier's law. And this guy we can get from Newton's law of cooling, right? We have those rate equations from chapter 1, and that puts it into terms of temperature. So we end up with however many more additional equations we need to solve for those extra unknowns. Okay? And so it just becomes a matter of solving those simultaneous equations. However, I left off last time saying, if we're dealing with convective cooling at the edges of a cylinder, it gets kind of messy. And so we're going to see today a nice, very, very efficient approach for accounting for when you have a lot of different boundaries with different conditions all combined together. Before we do that, so that's what's known as resistance concepts, and I've mentioned this previously. Okay, but it's one of the more intuitive tools in heat transfer, and I think you guys are going to pick up on it quickly. But first, I just want to quickly we've sort of beat this 1D conduction thing to death, right? So I'm going to just go through sort of the stencil of how we do it in spherical coordinates, but I'm not going to spend a lot of time belaboring the point. So quick reminder on what spherical coordinates really are. Right. This is probably something that is old hat to everyone in here, having done some dynamics and physics, but right, the idea is if you have your XYZ coordinate system, we'll say X, Y, Z coordinate system, then some point in space is going to be, of course, defined by X naught, Y naught, Z naught, right? The alternative representation, if we're talking about spherical coordinates, would be draw a line straight to that. That line has length r. If we project that line down into the xy plane, its angle in the xy plane is called phi, and then the angle of deviation from the vertical is known as theta. And so that point can alternatively be stated as r theta, or sorry, r naught, phi naught, theta naught. So there are transformations between the two coordinate systems. Those are to be found in any dynamics book, any kinematics book. But the idea is when you're working in this coordinate system, our derivatives are a little bit different. Okay, there's typically an extra 1 over r, okay, or 1 over r squared when dealing with cylindrical coordinates, and the reason for that is dimensional homogeneity. So let's imagine that we have, right, this looks kind of like our cylinder from before, but I want to imagine that this is a cross-section through some spherical shell. Okay, so it's got some, right, we measure r in any direction outward from the center here. And the assumption is that we're dealing with steady heat conduction again. T is a function of r only, meaning it's one-dimensional, and we're neglecting heat generation. Okay, so these are the three kind of killer assumptions that we make that take our heat equation here down to a much more manageable form. Speaking of this heat equation, right, you can see the ramifications of working on a different coordinate system in the 1 over r squared, these sine theta terms that pop up throughout our various derivatives. Okay, these come from the differences in that del squared t term that's in our heat equation if we wrote it in vector format. So this can be found in your book. I think it's equation 228 or something. I'm not going to make you go through the derivation of this form. But the idea is, let's start working through our assumptions one at a time. If we look at steady heat conduction, right, it means get rid of all the ddt terms. So over here on the right-hand side, that goes away, takes care of steady. T is a function of r only, means that basically any dd theta or dd phi terms equals 0, which means get rid of that guy, get rid of that guy. So that takes care of our one-dimensional assumption. And then no heat generation means this q dot term gets canceled out too. So what we end up with is 1 over r squared ddr k r squared dt dr equals 0. Looks kind of similar to the version we worked with in cylindrical coordinates, but now instead of just a 1 over r and an r, we have those r's to the second power. If we make the assumption that we're dealing with a homogeneous material, which is usually the case in this class, k doesn't vary as a function of r, so k will come outside of this derivative, and we can actually cancel out. We can divide through by k over r squared, which will get rid of those terms. And our sort of simplified heat equation that we actually seek to solve would be ddr r squared dt dr equals 0. Okay. Almost done here. If we were to take, now if we're taking this and we want to solve it, right, it becomes, once again, a matter of integrating once, get this term out, dividing through by r, integrating again. So if our equation to solve is ddr r squared t del r equals 0, integrate once, we end up with r squared t dr is equal to some constant, divide through by r, t to r is equal to c1 over r squared. Sets us up to integrate again, and we end up with t is equal to negative c1 over r plus c2. So this is our general equation, right? Or our general solution. Once again, we are seeking to use information about the boundaries to constrain our constants of integration here. We haven't made any assumptions about fixed temperature, about convection, about radiation conditions at the edges. This is completely independent of what's going on at the boundaries of our, of our spherical shell. This is only a function of the shape of the domain we're trying to solve it in, and then the specific form of t, or the specific values of c1, c2, are going to be constrained by whatever conditions we impose. So that's the important thing to remember, is that for all of these cases, our general solution is completely independent of the boundary conditions. So finally, let's say we did specify boundary conditions at radius 1 and radius 2. Once again, it would just be a matter of plugging those in, saying that t at r1 is equal to ts1 and t at r2 is equal to ts2. We're not going to walk through the algebra this time because this is trivial, but what we end up with is that c1 is equal to ts1 minus ts2, 1 over r1 minus 1 over r2, and c2 is equal to ts1 plus over r1 or ts1 plus ts1 minus ts2, r1 minus 1 over r2 times 1 over r1. So these are the constants for fixed for fixed temperature boundary conditions on the spherical shell. So we could, of course, plug these guys in here to get the expression for temperature, but I'll go ahead and summarize that along with our other results that we've come up with so far. So right here we've got, the cases we considered: the plane wall, the cylindrical wall, and the spherical wall or spherical shell. Okay, these are all one-dimensional. In the case of the plane wall, t is a function of x, distance across the wall. Cylindrical wall, t is a function of r, and the spherical wall, t is also a function of r, right? So we've got the version of the heat equation that we seek to solve. Once again, this is for no heat generation. That doesn't show up. Black on black doesn't show up very well. That's for no heat generation and steady conduction. Okay, so this is the simplest of all cases with the heat equation. So we end up with our dt dx equals 0, the cylindrical version, and the spherical version. When we go through and we solve for those, okay, we go ahead and let's assume that we have that information about the temperatures at the surfaces. Okay, the constant temperature boundary condition. Plugging those in, we get these expressions for the heat or the temperature distribution across those walls. So it's a function of Ts1 and Ts2, where in the plane wall, that means Ts1, Ts2. In the cylindrical wall, right, that would mean Ts1 at the inside radius, Ts2 at the outside radius, and in the spherical wall, Ts1, Ts2. And so finally, we have the temperature distribution, and if we apply Fourier's law, right, which allows us to take the slope of these temperature distributions at any point to get the heat flux, and then multiply that by the local surface area to get the heat rate, we end up with these expressions. All right. Quick sanity check. The heat rate has to be, because of the way we define the problem, has to be constant across the thickness of the wall for each of these cases. So that is, yep. So note that in none of these expressions do we have anything that's a function of r. Okay, we have r1 and r2, which are the radii of our inside and outside boundaries, but everything is essentially just a number, which is as it should be. So that tells us that the heat entering one of these walls from one surface all has to travel through that wall and leave through another surface taken through that wall. Okay, it's conservation of thermal energy. So the other thing that's nice about this, okay, is that because this heat rate, right, basically all of these terms have something that reflects the difference in temperatures between the inside and outside. It's basically some constant times that temperature jump. So this leads us to what's going to be kind of the main takeaway from today, which is now it's known as the resistance analogy. So let's kind of jump trains of thought here for a second and go into electrical circuits mode. Remember the concept of an electrical resistor, right? Basically, it's the sign we use to represent a resistor, and we say it has some electrical resistance R sub E. We'll also say that it has some voltage potential at each of these ends, V1, V2. And assuming that V1 is greater than V2, what's going to happen is it's going to push some current through the resistor, right, which we denote as I. So Ohm's law, right? Ohm's law tells us that I is equal to V1 minus V2 over RE, right? The jump in voltage potential from one side of the resistor to the other divided by the electrical resistance gives us the current that's allowed to flow through. Or we define the resistance by just rearranging this equals V1 minus V2 over the resulting current that flows through. Right, this is all pretty simple. Fine. Electrical resistor. What about if we swapped out these V's for temperatures and I for Q? Okay. The idea behind a resistor, or behind the electrical circuit, is that the current going in one side has to all come out the other. Right? There's a sort of this conservation of current. It's called Kirchhoff's current law. We have a similar thing going on in thermal flows, right, where the sum of the heat in has to equal the sum of the heat out. And this thermal conductivity tells us something about how easily heat flows through a medium. So if we look at this thing called a thermal resistance, it's essentially, we draw it out schematically the same way. We use an electrical resistor to represent it, T1, T2. We'll give it some sign R. And what we have flowing through it this time, instead of current, is Q, or in some cases, Q double prime. So in this case, we say that Q is equal to T1 minus T2 over that thermal resistance. Okay. Or we decide to define that thermal resistance as T1 minus T2 over Q. And since I mentioned this Q double prime, right, sometimes Q is the total amount of heat flow, right? But if we don't have information about the surface area of some object, sometimes it works better to work in heat flow per unit area, which is our flux resistance then is just equal to basically T1 minus T2 over Q double prime, and the Q double prime over Q is just A, right? So this works out to T1 minus T2 times the surface area over Q. Okay, so if we sort of quickly at this point, if we take a look back at that previous table, right? The idea here is we look at our heat rates. I mentioned that there's this idea that we have this constant times that jump in temperatures, right? So these right here give us they give us all we need to know about how we would represent each of these sort of types of walls as a thermal resistor. Okay? Because if we factor out that TS1 minus TS2, then everything that's left behind basically is a 1 over R. So we're going to concentrate first on the plane wall, and then we'll come back and we'll look at the radial systems. The idea with the plane wall is, right, we had that Q is equal to Ka over L times TS1 minus TS2, which tells us that R is equal to L over K times A, right? That is if you have a wall of some given material, right? If your thermal conductivity is K, this is pretty intuitive. If you were to make that wall thicker, okay, if you were to increase L, then your thermal resistance is going to go up, which means you get less heat through it. Seems fair. At the same time, if you were to make the surface area of the wall larger, okay, then you're going to be able to transfer a larger bulk amount of thermal energy through it per unit time with the same temperature jump. Also seems fair. So we get the right kind of physical behavior out of this. This makes sense. And then if we wanted to represent the flux resistance, again, this is just equal to L over K. All right. What is really, at this point, like this, it seems hardly worth the effort, right? The L over Ka or L over K, that's an easy enough thing to plug in anyway. This result right here is not terribly cumbersome to use. Where this thermal resistance concept becomes really valuable is when you have what's known as a composite wall. So imagine that we take a plane wall and we stack on another plane wall and we stack on another plane wall on that. Okay, we'll say that each one has some and I have awesome. I have lost my ability to write. All right, just a second. There's all my writing. All right. So we'll say that this first wall has some thickness L1. Second one has a thickness of L2. Third one has a thickness of L3. Okay. Additionally, they're each going to have a different thermal conductivity. We'll have K1, K2, K3. So, if we wanted to solve this the way we've been doing for the last week, right, we would say, all right, each of these can be treated as a plane wall. So inside of each wall, we would end up with that T equals C1x plus C2. All right. And what we would have to do is basically say, even if we know, let's say we know TS1 and we know TS2 over here. What we would have to do is to find the intermediate temperatures, we would have to specify a flux boundary condition. Basically, we would say that Q double prime leaving this wall due to conduction is equal to Q double prime entering this wall due to conduction. Okay, and then Q double prime leaving this wall due to conduction is equal to Q double prime entering that wall due to conduction. And so that would give us several extra equations to solve for those extra unknowns, right? Which turns into a mess really fast, especially when you're dealing with highly engineered composite walls where you can have hundreds of layers stacked on top of one another. It's just not feasible. So let's continue just making some assumptions here. Let's say we have the surface area equal to A, and okay. So the idea here is if we instead choose to represent each of these walls as a thermal resistor, okay, we'll say we have some node at TS1. We have the resistor that represents that wall, T2, T3, TS. You know what, we'll call this TS4. Okay. Why would this be a valid way of solving this problem? Well, just because in electrical circuits, right, the idea is that Q in this side has to be equal to the Q passing through every component of this wall. So Q out. It's constant, right? We've already established that. Which means that we're going to end up with, if there's a Q, a current passing through each, if there's a heat rate passing through each of these walls, we're going to end up with these temperature drop associated with section 1, temperature drop associated with section 2, temperature drop associated with section 3. So what this is going to look like is this. Again, this shows us why it would be a pain to essentially solve for those three linear distributions at a time. Okay, it's unnecessarily cumbersome, because if we were to say, all right, the same amount of current is passing through here, then the voltage drop here is going to be equal to, right, that basically TS1 minus T2 by our thermal resistor analogy is going to be equal to, right, Q over R1. And so delta T2, which is just T2 minus T3, would be equal to Q over R2. And delta T3 equal to Q over R3. Moreover, if we were to say TS1 minus delta T1 minus delta T2 minus delta T3, basically that would be TS1 minus TS1 plus TS2 minus T2, or T2 plus T2 minus T3 plus T3 minus T4. That's the idea, is that eventually what we're going to get out the other side is TS4. So the takeaway here is that if we said TS1 minus TS4 ends up being equal to Q 1 over R1. Oh, sorry. That is not quite correct. That's supposed to be times R3. My mistake. R1 plus R, and they should all be multiplied. 2 plus R3. Or, alternatively, Q is equal to TS1 minus TS4 over, right, the sum of all of our individual resistances. So, takeaway here, if you're stacking up walls in a composite fashion and you are transferring heat through those walls, you can treat it like it's a series circuit. You can add those thermal resistances together. All right. So the idea is that this is going to save us significant amounts of time, because it's very easy to compute R1, R2, R3, right? Each of those is just a function of K, A, and L. And it'll save us a lot of time when what we're really concerned with is either the temperatures at the extreme edges of the wall and or the net heat rate flowing through the wall. And I saw a question.
Sorry,
yeah. Sorry, that's supposed to be a summation. Yeah. So, in a nutshell, very useful when T of X is needed, right? This isn't going to give us the temperature distribution. What it's going to give us is the bulk effect of the wall. So, so we've established at this point, right, if we have some TS1, TS2, said that at TS1 minus, or sorry, TS4, TS1 minus TS4 is equal to Q times what we call R total, where R total is just equal to the sum of all individual resistances of objects that the heat is flowing through. So Qx equal to TS1 minus TS4 over our total. And I wanted to point out that if, for some reason, as I said, like if a problem that we're considering has this, but we don't actually have the surface area of the wall, okay? Remember that like R1 here would be equal to L1 over KA. If we don't have the surface area of the wall, instead we would opt to use R double prime 1, which is just equal to L1 over K1, right? And the way we would use that is TS1 minus TS4 we could just use the same sort of approach where R double prime total is equal to the flux resistances of each element. So just two ways of talking about it, either including the surface area or not including the surface area. Final note here, and then we will do an example. What if we have a non-constant temperature boundary condition? So if we have, right, the idea is we've said like our temperature distribution is going to look something like this. We're going to have some surface temperature, so TS4. What if we don't actually know the values of TS1 and TS4? Instead, what we know is that there is some, for example, some hot and cold regions of air with, say, T infinity 0 and some convective heat transfer coefficient H0. And over here we'll say this is at T infinity 5 with some convective heat transfer coefficient 5. We know, right, instinctively that our temperature distributions are going to look something like this, right? We're going to get that convective cooling. But how do we build this into this idea of the resistance network? Turns out Newton's law of cooling is already is tailor-made for a resistance representation, because Newton's law of cooling states, in this case, that Qx is equal to H T infinity naught minus TS1 times A, right? That would be the amount of heat flow in through the left-hand boundary. Okay, so what if we wanted to come up with the equivalent resistance? We would say that R is equal to T infinity naught minus TS1 over Qx, which is 1 over H times A. All right, what does this do for us? Well, it allows us now to treat the heat transfer across this boundary by convection not as a boundary condition, but as just an extra resistance element. Okay, so when we're stacking up all those different resistances, we say that this one has R1, this has R2, this has R3. Now we can include there that we have at this boundary some R0 and some R4, okay, where these guys are all conduction resistance And these guys are convection resistance. So our total resistance network now would look like R total is equal to R naught plus R1 plus R2 plus R3 plus R4, which is just 1 over H naught A plus, in this case, the resistance for the conductive wall, then going to be L1 over K1A plus L2 over K2A plus L3 over K3A plus 1 over H5A. So, assuming we know the convective heat transfer coefficients, H naught out here in the hot air and H5 out here in the cool air, and assuming we know surface area, and assuming we know thickness and thermal conductivity of each layer of the wall, we have all the information we need to calculate the bulk heat flow through that composite wall. Or, if we know the bulk heat flow, for example, there's a problem on the homework, where you have an electric motor that's generating a set amount of heat, regardless of what you do with that heat. Okay. Let's say that you have a situation like that, where there's a constricted amount of heat flowing through a wall. With this approach, you can then calculate the temperature difference from one side of the wall to the other. Okay. So it's a very elegant and practical approach to conduction analysis. So let's go ahead and wrap it up with a quick example, and I think we'll be in good shape. So we're going to talk about gas turbines. Okay. So this here is the General Electric LM6000. This thing generates 50 megawatts of power. Those of you not aware, that's around 60,000 horsepower, and the object is the size of a car. So the idea is that these things generate and extract huge amounts of thermal energy, and they do so by combusting air up here, it's the Brayton cycle, combusting fuel and air mixtures, form really high temperatures, and blowing that through multi-stage turbines, which extract essentially the pressure energy of that air flowing through and turn it into mechanical work. So one of the issues is that this hot gas coming out of these combustion chambers will reach, well above 1,000 degrees Celsius. So in this case, we're considering that we have hot air at 1,700 Kelvin, which is 1427 degrees Celsius, which is really, that's a little too hot for most of the alloys that we like to make these blades out of. So one of the approaches has been to use air cooling, where you blow cold air through the inside of the blade, as well as this thing called a thermal, what do they call it? The thermal barrier coating. Of some lower conductivity metal bonded to the outside to act as a heat shield. So what we're asked to do here is say we're given temperatures for the hot gas outside, temperature for the cooler gas flowing through the inside, as well as the blade material, which is Inconel alloy, for the given thermal conductivity. This thermal boundary coating, thermal barrier coating rather, is this zirconia ceramic with a much lower, only around 1 watt per meter Kelvin, and a very thin layer, only 0.5 millimeter thick. Additionally, we say that these two are bonded together with this metallic bonding agent, and this bonding agent itself has some thermal resistance, which is just given to us as a number. So this is another nice thing about this resistance concept, is often at things like boundaries and bonding agents, you'll just be given a resistance to plug in. So the question is, in the end, are we going to melt the blade? Is it going to exceed this maximum temperature of 1250 Kelvin, which is where we begin to see failure of the Inconel material that makes up the blade? And we're told, go ahead and use a plane wall approximation that amounts to saying that the curvature, that the thickness of the blade is small enough relative to the radius of curvature that we don't see those that the heat in one side doesn't get much of a chance to spread out before it leaves the other side. So to set this problem up, we're going to go ahead and imagine we have our section of the blade. So over here we have, right, the blade wall at 25 watts per meter Kelvin is K, and it's going to have some temperature TS3. We're working kind of backwards here. At the boundary here, we've got this bonding agent with a flux resistance given to be 10 to the negative fourth meters squared Kelvin per watt. And then we have our thermal barrier coating, or TBC, which has K of 1.3 watts per meter Kelvin, and is presumably at a significantly higher temperature, TS1. So out here we've got our hot air. We'll call this T infinity O for outside, which is equal to 1700 Kelvin, and has a convective coefficient of 1000 watts per meter squared Kelvin. And out here we've got cooler air blowing through the inside, so we'll call this down here, we'll call this TSI, is equal to 400 Kelvin and has an H of 500 watts per meter squared Kelvin. Okay. So I think where we're going to get today is basically we can set up the resistance network, because that'll only take up a second, and then we'll use this to jump back into wrapping up resistance concepts in the next lecture. In the top left, up there? Yeah. That is an H. That's an H. Yes. Because out here we're talking about the convective coefficient as opposed to conduction. So our resistance network here is going to look like our first node represents what temperature? It's going to be T infinity outside. All right. We're going to have a resistance that represents that convective heat transfer between the air and the wall. We have then our next node is at surface temperature 1. Then we're going to have this conductive resistance, okay, inside of that ceramic coating, the TBC. Then we're going to have essentially this, we'll call this R12. This is the thermal resistance of this bonding agent between the two layers of material. Okay, and this is the thing that we've been given. We've been told there's this layer of glue in there that has some resistance. I should put double primes over all of these because we're going to work in heat flux. And then we're going to have another resistor, which is R2. That is the conductive resistance of the Inconel blade wall. And then finally, we'll have our last resistor, which is R3. And we end up with our inside air temperature. And so in each of these cases, right, we don't have any information about the area of the blade, right? We haven't been given A, which is the reason that we're using the heat flux resistance. So we're talking about watts per meter squared remaining constant as we travel through rather than watts itself. So the idea here is, once again, we already have all the tools for convective heat transfer. This is just going to be 1 over, in this case, H. We'll say H outside. This resistance is going to be 1 over H inside. And then each of these, right, this is just going to be equal to L over K for each of these three, or for these two resistances, and then this one's been given. And so you just calculate those, you add them up, you get the total resistance, and then, right, the idea is we have all the information we need to find the temperature of the blades. But we will finish solving this problem on Monday when we pick up the rest of the stuff. Yeah.
So temperature rate.
Huh?
You put a dot over the last temperature. So is the answer a rate or is it?
I don't know. I did not mean to. I think that was just an errant pen stroke. No, that is not a rate.